Hi, today we're going to talk about the relationship between standard reduction potentials and free energy. So we ended our previous video by asking whether a redox reaction would be spontaneous, and I stated that it would be spontaneous if the E0 of a reaction was greater than 0. We're going to look at applications of that and what that actually means. When we were looking at standard reduction potentials, I mentioned that the higher the standard reduction potential, the E0, the more likely a substance would be to be reduced, and the stronger an oxidizing agent it would be. In other words, the more likely it would be to grab electrons off of another substance. Likewise, the lower your value of your standard reduction potential, the more likely that substance would be to be oxidized, and the stronger a reducing agent it would be. And that just basically means the more likely it is to give up electrons. We made those statements about single standard reduction potentials. And now let's talk about what that means when you're putting half reactions together to make a whole redox reaction. For a reaction to be spontaneous, you need that half reaction that has the larger standard reduction potential to be the reduction reaction. And that goes along with what I just said about individual half reactions. The more positive something is, the more likely it is to be reduced. The half reaction with the smaller standard reduction potential is going to be the oxidation half reaction, because remember, the lower that standard reduction potential is, the more likely something is to be oxidized. So now let's talk about the mathematical definition of spontaneity. We've just said that our E0 allows us to predict whether a redox reaction is spontaneous. We also know delta G is a measure of spontaneity, and that means there has to be some sort of connection between the two of them. And this is what it looks like. The delta G of any redox reaction is going to be negative N times F times the cell potential for that reaction. So we know what delta G is. We've talked about that a lot. We know what E is because we've been talking about that a lot today. Let's look at what else we have in this equation. We've got an N, which is the number of electrons per mole of reaction. And we will come back to that when we work problems. And we have this constant that we call Faraday's constant. It's basically 9.65 times 10 to the fourth coulombs per mole. You can get it to more sig figs if you look in your book, but it's rare we have more than 3 sig figs, so this is usually sufficient. So what I've given you here is a generic reaction, but let's think about what happens under standard conditions. At standard state, we're going to have not just any delta G, but delta G naught. That's delta G at standard conditions. And our cell potential is going to be E0, so it's going to be derived from the standard reduction potentials. And yes, I basically took the same equation and I added 2 little naught superscripts on them. And yet that makes a big difference, as we will see tomorrow. So for today, we're just dealing with standard state conditions. And basically, here's what you're going to do if you want to get the delta G naught for a reaction. You're going to first balance the redox reaction. That ends up being very important because we need to get that number of electrons. The second thing is calculate the E0 of the cell using our standard reduction potentials, just like we did in the previous video. And then the third thing is we're going to calculate our delta G naught using the relationship that I just showed you earlier, delta G naught equals negative NF E0. Okay, so here we're going to find delta G naught for a reaction between aqueous silver ions and solid copper. And we're given the products. And so we're going to start off by balancing our redox reaction. And to do that, we first need to write half reactions. We see that we have 2 things with silver in them. So we have Ag plus becoming Ag. And to balance that half reaction, we need to add an electron so that the charges balance. And then we also have a reaction involving copper where we're turning solid copper into copper 2 plus ions. And again, this is not balanced because of charge. Therefore, we need to add electrons. And that's what that looks like. In order to make a balanced redox reaction, we need to combine these, but we can't combine them until we have the same number of electrons in each half reaction. So we're going to be multiplying this one by 2. And then at this point, because now both of our half reactions have 2 electrons, we can go through and we can add them together to get an overall net reaction. But we can't forget that we had 2 electrons per mole of reaction. This is what that means. 2 electrons come off of copper and go on to silver. So that 2 is going to be our number for N in our final equation. So let's hold on to that number. And now we're going to take our original half reactions before multiplication, and we're going to use those to look at the table. We have silver ions being reduced to silver, and we can find that here. That has an E0 of plus 0.80 volts. And we have copper turning into copper 2 plus ions. The closest we can find is this one, plus 0.34. But if you compare this to the one in the table, you'll see that this is running in reverse. Therefore, this is our oxidation reaction. And so now we can take those numbers, we can plug them into our equation for the cell potential, and we get 0.80 minus 0.34 equals 0.46 volts. So now we have our cell potential, we have our N, we have the number of electrons for our balanced equation, and now we can calculate delta G naught. And that's going to be -2 times Faraday's constant. Note the units on this, it's coulombs per mole, times 0.46 volts. Now, if you look at those units, they don't seem to make sense. Nothing seems to cancel. So let's remember that volts actually equal joules per coulomb. I'm going to replace that there. And now you can see the coulombs are going to cancel, and we're going to end up with units of joules per mole, which are really great units for a delta G number. So it's 88,780 joules per mole. And if you want to convert to kilojoules, you can get 89 kilojoules per mole. That has an appropriate number of sig figs. Here's one that is a lot harder, but if you ever do problems like this in an industrial or environmental setting, a lot of times you won't have 2 balanced half reactions. So here we're looking at the reduction of permanganate to manganese 2 plus. The problem says by water, which means that water is the reducing agent. Water is being oxidized. And so what you have to do is you have to go through and you have to find something where water is the final product of your reduction, because you know if that's the oxidation reaction, that is going to have to be flipped around. I don't know if that makes sense, but let's write these out. Now, it's possible that you can take your permanganate and your manganese 2 plus ions, put them on opposite sides of the reaction, and then go through and balance that half reaction the way you were taught in Chem 1. But if you have that half reaction in your table of standard reduction potentials, they usually have a balanced half reaction for you, as you can see down here. And so to balance our redox reaction, we can just take that balanced half reaction from the table. And then I went through and I picked out this one half reaction that seemed the most appropriate. And so we have water being oxidized to oxygen H plus and 4E minus. Now, when we try and put these half reactions together to make a whole reaction, we need to end up with the same number of electrons. And that is not easy, because here there's no integer we can multiply to turn 5 into 4 or 4 into 5. So we're just going to have to look for the least common multiple. We're going to multiply this one by 4 and this one by 5. That will give us a total of 20 electrons. Now, I don't actually have to write the final balanced redox reaction, as long as I know how many electrons we need to make that balanced redox reaction, because that's all we really need for our delta G naught equation. Here are our 2 half reactions along with our number of electrons, and now we're going to figure out which is which, even though I've kind of talked you through that already. We have our reduction reaction is going to have an E0 of 1.51. our oxidation reaction, and we know it's oxidation because it's reversed from what we see in the table. Our oxidation reaction has a standard reduction potential of 1.23 volts. And so when we calculate our cell potential, it's going to be 1.51 minus 1.23, and that gives us a value of plus 0.28 volts. Now we have our cell potential and we have our number of electrons. Let's go ahead and plug that into our delta G equation. Plugging in the numbers we have, and again, I've just gone ahead and straight out written the plus 0.28 volts as plus 0.28 joules per coulomb, so our units work out. We end up with 540,400 joules per mole, or 540 kilojoules per mole. We have just talked about how delta G is related to the cell potential, but we also know that delta G is related to the equilibrium constant, and this tells us that our cell potential must be related to the equilibrium constant. So if both of these things are equal to delta G naught, then we can set them equal to each other, and that's what I've done here. And now what I'm going to do is I'm going to divide both sides by negative NF, and I get this. The cell potential is going to equal RT over NF, natural log of K. So now we have a direct relationship between our cell potential and our equilibrium constant. So if we want to calculate our equilibrium constant from our cell potential, we're going to do a similar process to what we did before. First, balance the redox reaction, focusing on finding the number of electrons in a mole of reaction. Second, calculate our cell potential using standard reduction potentials from our table. And third, then taking those numbers and plugging them in to our equation. Now, right now we have that written as E naught of the cell equals something times the natural log of Kc, but we can do things the other direction as well. We can calculate Kc from the cell potential value. So let's go through and do something. Here we're going to reduce copper 2 plus to copper metal by using water again. So this is going to be the same oxidation reaction that we had before. Let's find the number of electrons in the balanced redox reaction. Here's our reduction reaction. Copper 2 plus is being reduced. It's gaining electrons to copper metal. And then we have this same oxidation reaction that we pointed out before. And you can see that we have different numbers of electrons in our two half reactions. But what we can do is multiply the top half reaction by 2, and that will give us a total of 4 electrons, and we will be even. So 4 electrons is what are exchanged in our balanced reaction. Now we're going to calculate our cell potential. What are our standard reduction potentials? For copper, the reduction potential is plus 0.34. This one again is plus 1.23. Remember, that is the oxidation reaction because it's reversed. So we can plug that into our cell potential equation. We have 0.34 minus 1.23, and that gives us a cell potential of negative 0.89 volts. Now that we have both our cell potential and our number of electrons, we can calculate the E naught of our cell. Here's our equation. We can plug in the numbers. You'll notice that this includes 2 different constants, the Faraday constant and also R, our gas constant. We're going to use the 8.314 joules per mole Kelvin, since this is related to energies, and we have, for example, joules over on the other side of the equation. Let's solve that then for the natural log of K. What we end up with is natural log of K being negative 138.59. So then the equilibrium constant is going to be e to the minus 138.59. And that's going to be 6.5 times 10 to the minus 61. Now that is a really tiny number. What does it tell us about this reaction? Well, when we look at our cell potential, we see that it is less than 0. And that tells us that it is not spontaneous. When we look at our value for K, we see that it is very small, which means that the reactants are favored. So another way you can think about this is if you put together water, copper 2 plus, and copper, what would actually happen is the reverse reaction where we would reduce oxygen to water and oxidize copper to copper 2 plus. Standard reduction potentials aren't just something that we use when we want to, build a galvanic cell and hook our voltmeter up to it. They are actually useful for helping us calculate whether something will be spontaneous and what the equilibrium constants will be for a particular reaction. I hope this was helpful, and I will see you again soon.